Okay, so in one more setup comment before we start. Some of what we're going to say, it's going to be easier to state things for homogeneous models. So a homogeneous model of order D means that for any positive constant C, if I scale the parameters, all the parameters by C, I scale my function by C to the power of D. Okay? And you can think of D as a depth in some sense, which is why it's both degree and depth, right? So a linear model is homogeneous with order 1, right? If F is some kind of factorization, so say U times V, and I'm being a bit not specific here about what I mean by product here, right? But now if I scale both U and V by 2, then U times V gets scaled by 4. If I scale U and V by C, then this scales by C squared, right? And more generally, if we have a network of depth D and all the activations are homogeneous, so all the activations are either linear or ReLU, so a depth D ReLU network is homogeneous with parameter corresponding to the depth. Okay, so with that setup, we want to understand what's going on here, and in particular, the type of questions we want to answer. So ultimately, we want to be able to kind of describe this implicit bias, build a language to describe this implicit bias, and understand how can we connect it to what we talked about before about optimizing here with respect to some metric tensor and identifying the potential. But also two questions we'll try to answer, more kind of high level. One is this equivalent to explicit regularization? So we saw that for gradient descent on a linear model, gradient descent on a linear regression, then what it converges to is a minimum L2 solution. So doing explicit L2 regularization is the same as what I get from gradient descent. And is this all what's going on here? If I'm doing gradient descent on the parameter space, is it just equivalent to regularizing the L2 or Frobenius or whatever norm of W, like we saw, for example, in the last lecture, today, not my last lecture. Okay? And if I'm asking that question, you can already guess that the answer will be no, and we want to understand in particular in what ways these are different. Okay? And the second question, we heard quite a bit in the past few lectures by both Andrea and Chaim on the kernel regime. Okay? So you can, in certain regimes, you can think of you can approximate the behavior of your model or of the neural net as a kernel. And basically what that just means is that if we look at oops, why am I in yellow? Okay. If I look at the function computed, if I look at the model or the function computed by the model, I can always write its linear approximation, right? So f of W naught x. So the linear approximation about the initialization plus W minus W naught times the gradient at initialization, which I'm going to refer to as, okay, oh, thank you, is phi naught, okay? Right? So all we wrote here is a first order approximation for our model, you know. And the thing is that in certain regimes, we always stay within this linear, so this linear approximation remains valid. We kind of always stay, turns out that throughout optimization, we always stay close enough to W naught that we can just work with this linear approximation. Okay? And that's a bit disappointing in some sense because that means that our model just behaves like a linear model. There's no point in all this like neural net stuff, right? In particular, in this case, we know exactly what the implicit bias will be because we understand the implicit bias of gradient descent on linear models, and what we'll get is just the minimum norm solution with respect to W, or if you want to think of it as a kernel, right? So I wrote it here with an explicit feature representation. I can always write, write things either using explicit feature representation or with the corresponding kernel. So the corresponding kernel here would just be the inner products of these features, these feature vectors. And so in terms of this current, in parameter space, I'll converge the minimum norm solution, minimum L2 norm solution. We know the L2 in parameter space corresponds just to the corresponding RKHS norm in feature space. I think Andrea discussed this a bit. So then we know that gradient descent will converge to just the minimum the function that fits the data that has that's minimal norm in our RKHS. And I should say here, it's not really H, it's H minus H naught, right? Because we converged in gradient descent, we converged to the, not to the minimum norm, but the minimum norm distance to initialization, right? So H naught here is just the function parameterized by our initial point. But we'll see in a second, we'll generally want to kind of avoid talking about this. We'll use initializations where at initialization we have the zero function. So we initialize at the zero function, so we can avoid this. And this, from my perspective, is a bit disappointing because, again, I mean, if we're studying a regime which just boils down to finding a minimum norm, and doing a kernel ridge regression in some sense, a kernel ridge regression, we don't need all this neural net stuff. And if that's really the answer, then either we're studying maybe a non-informative regime, or maybe we could just replace neural nets with kernels. So in what case do we get this kernel regime? So there, I think at least the term neural tangent kernel initially was related to having when the width goes to infinity, and we also saw it in Haim's presentation. He also took the width to infinity to get into a Gaussian process, which is also a kernel regime. But I think from our perspective, more informative is actually the observation of Chizat and Bach that that I think Andrea already mentioned, which is that for homogeneous models, we can also, regardless of the width, for even with a finite model with a finite number of parameters, we always get to the kernel regime when the scale of initialization goes to infinity. Okay, so we'll look at where do I want to write it? Let's do it over here. Okay, so let's. Okay, so in order to describe this, and from the rest actually, or not the rest, but most of the talk, we're talking about gradient. We talked about gradient descent, but we'll move to we'll move to an infinitesimal step size limit to gradient flow. We'll mention finite step sizes in a bit. So really, we're talking about the dynamics given by dw dt is the gradient of the loss with respect to w, the empirical loss with respect to w. Okay, what we're going to want to do is we're going to initialize a different scale. So alpha is going to be our scale of initialization. Let's take alpha times some w naught. So w naught, think of it as some fixed, maybe random, maybe very simple. We'll see in the specific example, but this is for any w naught. Although in order to avoid these issues and also to make the kernel regime a bit simpler, we'll focus on w naughts, which in function space correspond to the zero function. Okay, so again, that doesn't mean the w naught is zero, and we'll soon see an explicit example. It's just the w naught maps to a null function in function space. Okay, okay, and we'll denote our differential equation with we'll put an index alpha here to remind ourselves that we're talking about how do the dynamics behave as a function of initialization when we initialize with some scale alpha. Okay, and I'll probably sometimes remember to put the alpha and sometimes not. When it's going to be important, I'm going to try to remember to put the alpha there. Okay, and the Chizat-Bach result can be phrased as following: that when I take this initialization scale to infinity, okay, then my entire trajectory after an appropriate rescaling of time, I think it comes to alpha to the d minus 1 here. Just converges to the trajectory of a kernel of doing gradient flow in the kernelized problem. So WK is just gradient flow on a predictor given by, let's write it this way, a predictor given just by a linear function on this phi of this phi naught. Okay, so this is just gradient flow in a linear function, in a linear on a linear problem. We understand very well. We know that it goes, as we wrote there, to the minimum norm solution parameter space, minimum RKHS norm in function space. And if we take the scale to infinity, we converge to it. And on the other hand, what we, in the first lecture, we saw how we get all kinds of very rich inductive biases that are definitely not RKHSs, like all kinds of things involving sparsity and nuclear norm and stuff that you can provably not get using kernels. And so we sort of are, to get them, we definitely are not in the in this kernel regime. And one of the things we'll see is how this initialization scale really controls, is a control parameter for which regime will be, whether we're in the kernel regime or whether we're this regime where the implicit bias is very rich. Okay, so in order to, so just to summarize our three questions that we want to address in this lecture are, one is how can you characterize the implicit bias and how is it related to this notion of information, of geometry of optimization and divergences in potential function we talked about. The second is it always just given by the L2 norm or can it be significantly different than that, L2 norm in parameter space? And the third is how is this related to the kernel regime, or what controls whether implicit bias is going to look like RKHS implicit bias or something else? Okay, and the model we're going to look at it, at least in the first half of this talk, we'll see how we go, is probably the simplest possible model in which you can already talk about some kind of rich inductive bias, talk about being in either in the kernel regime or not kernel regime. So I want to talk about a homogeneous model, right? Because first of all, these results are only for a homogeneous model, and also many other things become much simpler in homogeneous models. I can't have a homogeneous model of, so I can have a homogeneous model of degree 1, but that's just a linear model, that I already understand. So we'll go up to the next most complicated, next most simplest model, which is this homogeneous model of degree 2. Okay? So we'll write our model. It's just going to be a linear model, but with a, actually let's write it this way. So our model is just going to be a linear function of x, but instead of multiplying, instead of thinking of w as the coefficients, we're going to look, we're going to look at an element-wise squaring of the coefficients. Okay? So in other words, if I think of it in terms of a parameterization of my linear function space beta, I just look at a mapping from parameters to linear functions given by an element-wise squaring of the parameters. Okay? So this, if I want to draw it as a neural net, right? So this would correspond to a single hidden layer neural network with this diagonal structure. Right? So every, oops. Like this. Right? So every input coordinate goes into the output, but it gets, instead of getting multiplied by a coefficient, it gets multiplied by the coefficient twice. Okay, so this is W1, W2, and so forth. And the fact that I take these weights in the first layer and second layer to be identical, that actually doesn't matter. If I change it to U times V, nothing's going to happen here because due to symmetry, at least if initialized to be the same, they're going to be the same throughout. So that, I don't know if that bothers you, but it shouldn't. Okay? And this is with linear activations, right? So it's a depth 2 diagonal linear neural network. Okay, so we're going to modify this for two reasons. One is we want to say that we really can get any linear function. This is a parameterization of all linear functions. And I can't get any linear function this way. Why not? What linear functions can I not get with this parameterization? Sorry?
That are like the negative.
Yeah, I can get negative coefficients, right? My coefficients of my linear functions here, coefficients of beta will always be positive, right? Beta, W is real, right? Everything here is real, okay? So that's one reason that I want to change it. So I'm going to, in order to allow negative coefficients, I'm actually going to use 2D parameters. So W beta is in RD, then each of these is also in RD. Okay, I'm going to use 2D parameters, and I'm going to look at W plus squared minus W minus squared. Okay. And in terms of the neural net, that means that you can think of it, they have, for each coordinate, I have actually 2 units, and one of them with a negation. Okay. The other reason that I want to do this is because I want to be able to control the scale of my initialization while still always initializing to a 0 initialization, to zero in function space. Right? So I want to be able to have very large scale in parameter space and 0 scale or 0 initialization in function space. Okay? Doing this, I can do that. Right? If I take, we're going to take. Okay, let me. You'll remember that these are all in RD, and if I take W naught to be just the vector of all ones, okay? So that means that I'm going to initialize to the vector where all the initial weights are alpha. So I'm going to initialize all the weights to alpha, both the positive and negative ones. Then initialization, all the coefficients in beta are just alpha squared minus alpha. So at initialization, beta naught is equal to 0. Okay? And this is for any scale alpha. Okay? So we can initialize always at the origin in function space while still looking at what happens to the scale in parameter space. Okay? Okay. Is the setup clear? Okay, excellent. So now the question is, what is the what's the implicit bias of this network? What's the implicit bias of doing gradient descent on W? Okay, so using the this trajectory, how does it, in particular, how does it look like in function space, and where does it converge to? So we'll prove it actually in, we'll get the same characterization in 2 different ways. Okay, first we'll just try to do it explicitly by actually looking at the dynamics of W and arguing where we're going to get. So let's just look at how do W plus and W minus behave. Sorry. Okay. So let's just look at the dynamics in W plus and W minus. So the W dt is, where is it written? It's just the gradient given by the gradient of the loss on W. So just apply chain rule, right? So we have the gradient of the loss, let's write it this way, the gradient of the loss with respect to beta times the gradient of beta with respect to W. Oops. Okay, and we can evaluate both of these. So the gradient of beta with respect to W is just W itself, or maybe 2W the way I wrote it here. Okay. And the gradient of the loss with respect to beta, this is just the loss of a standard linear regression model, right? There's no, at this point, we're just talking about the standard linear regression model, and the loss, the gradient is just given by, and I'm going to warn you that I'm going to erase it in a second, by the residuals times x, and I think I have another factor of 2 from here. Actually, let's write it here. Accumulating factors of 2 here. Actually, or do I want to? Sorry, I'm not going to have a factor of 2. I'm going to think of, I didn't tell you what the loss is. So for simplicity, the loss turns out to not matter, but for simplicity, we're going to work with the squared loss. Okay, let's write it here. So loss y hat y is just going to be y hat minus y squared. Okay. So if the residual times x, and let's actually give that residual a name. So I'm going to call this RT. So R, we call, is just the residual at time t. Okay. Okay, and the same thing we can do for W minus, and we get just the result that everything is the same except I have a negative sign here because d beta d W minus is minus W minus, right? And so I get a positive sign here. Okay, great. So maybe we'll emphasize that this is beta t. Okay, good. Okay, so we have this these differential equations, and for now let's just take RT, the residuals, as known. Okay, so put the residuals aside, and if I know the residuals, then these are just linear differential equations, and I can easily solve them. Okay, so I can actually write down what W plus and W minus would be as a function of the residuals. Okay, so I get the W plus is just W plus initialization times exponential of minus 2x, yeah, right, times the integral of these RTs. So the integral from 0 to t of RT. And the same thing also for W minus. With a positive sign instead of negative sign up here. Okay? Great. So all I did was solve these linear differential equations. But, I mean, it seems like I didn't actually make much progress. So I can now describe my problem, you know, instead of solving differential equations, I have this, but this is still, I mean, this isn't actually a solution. This is actually an integral equation, right? Because RT itself is a function of W plus and W minus. Just forget the t's. Where am I? Minus y. Okay. And so all I did really was change my differential equations to integral equations, right? Because I have, you know, r is a function of w, and these equations involve an integral over r. But the thing is that this already allows me to say something quite significant about how the solution looks like. How? Okay. So in particular, let's go back to this, and let's look at how beta looks like. So I'm just going to write beta. You call it beta is just w plus squared minus w minus squared. So I'm just going to plug these in. And what we get is this is equal to the value of these h initialization, which is just alpha squared. Sorry, the value of each of these is alpha. So, okay, actually, maybe I'll do it slower. So this is equal to w plus 0 times e to the negative 2x transpose times this integral. And I'm going to call this integral st. So st, right here, is the integral of the residuals up to until time t. Okay. Minus e to the, minus w, there's a square here, minus squared times e to the minus, and I think I have a 4 here, right? Because I had 2, and I need to square it in order to, because I'm taking beta is equal to w squared. So I think this becomes a 4. 4x transpose the same this is plus. Okay, and these I actually know what they are. I mean, I just initialize them to all alpha, right? So this is just alpha squared. Okay. So what do we have here? We have an expression of beta, and it's still in terms of this integral of residuals. But note that this beta lives in RD, in a very high dimensional space, right? We're interested in underdetermined problems where the number of observations M is much lower than the dimensionality D, right? Otherwise, we wouldn't have to be asking these questions in the first place, okay? But we actually restricted beta to a low dimensional manifold of dimensionality M. Okay, so this is exactly what we did when we looked at gradient descent on linear regression. We said that just because no matter how I'm adding my gradients, just because I'm always adding gradients, and the gradients are always spanned on the data, then I'll always be in this m-dimensional linear manifold, okay, the m-dimensional subspace. The same thing happens here, except it's non-linear. So my dynamics, without even knowing anything about residuals, my dynamics are always restricted to this m-dimensional manifold of all the, let's write it explicitly, the m-dimensional manifold of all the vectors of this form for some S in Rm. Okay? And this should already be enough for us, because as we said before, we're restricted to an m-dimensional manifold. At the optimum, we're not, and as I promised you, I'm never going to prove to you that things actually converge to the global minima. But if we converge to the global minima, we converge to a zero solution. We also have that beta, that x beta is equal to y, right? So these are m additional constraints. We have m constraints intersect them with an m-dimensional manifold, and we're done. We have a single solution. Okay, so let's try to characterize what is that solution. Is this clear where we're going with this? Okay. Okay. So we're going to do exactly what we did before. We're going to try to match these constraints with the optimality conditions for a yellow optimization problem. So let's just write, just going to write it more explicitly as a constraint. I still want to, okay, so we have the constraint that beta is equal to something of this form for some S in Rm in this condition. Okay, and we want to match it to some problem. The problem is, unlike before, I don't actually have a good guess as to what my optimization problem would be. Okay, but let's just write it, where's my yellow, as minimizing some implicit objective Q, okay, over beta, subject to having zero error. Right? So this is kind of, I'm hoping here that I can actually characterize the optimum as the minimum Q solution, okay, for some Q. And what we're going to do is try to uncover Q. Okay? Okay, so let's write the optimality conditions here. So yeah, we had the, I call them KKT conditions. This is maybe a slightly degenerate form of KKT conditions. Maybe for you guys, they're obvious optimality conditions. Okay, let's write them. So we have that. So we'll have primal optimality, x beta equals y. And the Lagrangian is going to be, the gradient of Lagrangian is going to be 0. So the Lagrangian is going to be the objective here. I'm doing this a bit quicker because this is the same as what we did last time. The gradient of beta plus nu times the gradient of nu times the constraint, which is just going to be minus x times nu, is going to be equal to 0. Okay, so now let's rewrite this maybe this way. Okay. Okay, so we want to match these two conditions to these two. Okay, one of them is easy, right? So the primal optimality gives us this right away. Okay, so really what we want to say is that I can write beta. So some function of beta is equal to some linear function of the data. But look, that's almost what I have here, right? So I have here that beta is equal to some function of a linear function of the data. So all I have to do is invert this function. Luckily, I actually have names for all of these things, right? So I can actually do this sort of explicitly. So this, okay. So let's see if I have to say that when I encounter this, I have to start looking things up. because I can never remember which is which, but you're probably better than me. What is this function? Is a function of x transpose s?
Minus sin.
Right? Yeah. So this is just so alpha squared, right? And I think I had a 2 here. Okay, it's 2. So hyperbolic sine will be half of this, right? So this is just beta is 2 times alpha squared hyperbolic sine of 4, 2. Okay, now I'm going to get confused with that. What? I think it's 4 x. It of course doesn't matter, but let's just think it's 4. Okay. And I want to write x transpose s is equal to some function of beta. Okay, so all I need is to invert this. Okay, and I can write this as let's write it here. Okay, as the inverse hyperbolic sine of beta divided by 2 alpha squared is equal to maybe to x transpose times 4s. Okay, right? So now we see that we're really close to actually matching this condition. So on the right-hand side we have oh, there's a transpose here also. Right. Okay, on the right-hand side we have x transpose times our dual variables. Our dual variables will be 4s. Okay, that's fine. And now we just need to match the gradient of q with this inverse hyperbolic sine. Okay, so this would generally be a partial differential equation because we have a gradient here. Luckily, this when we wrote it this way, note that this is, we weren't very careful, but everything here is element-wise, right? Because all the derivation here, everything here was element-wise. So really, what we have here is a vector, is an m-dimensional vector, and we're applying the sine hyperbolic sine element-wise. And so this is just an element-wise function. I can really so here we have an element-wise function. So q is also going to be q is going to be of the form sum of I q. Okay, I'm going to change what q is in a bit, but it's going to be sum of I over some function of beta. Okay, let's call this q alpha of beta. Okay, because now when I take the gradient, I'm going to get an element-wise function, which each element is going to just depend on one element of beta. And so all we have to do is match q alpha of beta. Beta I. This is the ith coordinate of beta. Okay. Now all we have to do is match this scalar function. Let's call it. Okay. So beta is a vector here. B is a scalar. We have to match this with the derivative of this function with the hyperbolic sine. Okay. And this we can do. I mean, all we have to do is calculate the antiderivative. So all we have to do is integrate the inverse hyperbolic sine. Somebody remember the integral of the inverse hyperbolic sine? Oh, okay. Neither do I. I actually was surprised that it has a closed form expression, but apparently it does. So it turns out that the integral of so this is equal to, actually, I don't want to write the expression here because it's a long expression. I do want to write it at least once. Okay. It turns out that you can write, I'm going to need this a lot. Let's write it here. Okay. Okay. Actually, I'll write it twice. So this is going to be equal to, where is it? I had this expression somewhere. Where's my q? Oh, I have it. Okay, it's alpha squared b divided by alpha squared hyperbolic sine of b divided by 2 alpha squared minus square root of 4 plus beta I times b over alpha squared squared. Okay? So there's some expression, and this, sorry? This is this Q alpha, this is, oh, sorry. Okay, sorry, that's the integral already, okay? Okay, maybe I'll switch to, how complicated is to switch to the slides? I want to show you the plots of this. Okay, so let's switch to the slides. So the reason we're going to switch to the slides is because now we have a function. The question is, how does it going to look like, okay? So the first thing to do is to plot it, and that's easier for me to do on the slides. Okay, let me continue a bit in the slides and then we'll go back. It's, my computer thinks it's connected. Oh, okay, good. Okay, so my computer still thinks it's connected. Okay, okay, so what we got is that we managed uncovering the implicit bias. We characterized the limit point of gradient descent, and we characterize it as applying, this implicit regularizer Q, which is an element regularizer, which to every coordinate of beta tries to minimize this function. Note that everything there scaled with alpha, so you can just write it as a sum over the coordinates of Q times this function Q applied to the coordinate divided by alpha squared. So how does this function look like? Okay, so okay, I mean, great, I have a closed form for it, but what can I say? So let's first of all look at the two limits. So we said that the kernel limit is obtained when alpha goes to infinity. So let's see what happens when alpha goes to infinity. When alpha goes to infinity, the denominator here goes to infinity, and whatever the value inside here goes to 0. So I only care about the behavior of Q around 0. And around 0, Q is quadratic, right? So I can do that. Okay, I'm not going to do it here, but you can just calculate the first order. Take the second order Taylor expansion here. The first, the minimum is at 0, so there's no first term, and the second, I'm dominated by the second term. And around 0, the second term is non-negative, and so around 0, the function is quadratic, which means that if alpha goes to infinity, my regularization is effectively just applying some quadratic, the same quadratic to each coordinate. So I'm just having a sum of squares, or L2 regularization. Okay? And this matches, not surprising, the Chizat and Bach result, right? So we know that when alpha goes to infinity, we should be in the kernel regime. And in fact, we do get kernel type, the same type of implicit bias we would have gotten for a linear kernel problem. You can also calculate the tangent kernelization here directly. It comes out to be just the inner product between x and x prime, and so it's not surprising that the implied RKHS norm in linear space is just a standard Euclidean norm. Okay? The other extreme we can think of is what happens when alpha goes to 0. So that's maybe the more interesting one, when you initialize with very, very small alpha. So initialize with very small alpha, then again, what's going to be here is going to go to infinity. Okay? And so what we care about is only how this function looks like away from 0. Okay? And away from 0, this function becomes more and more linear. Okay? And what you get in that case is that you get effectively a linear regularization on each parameter, and you get effective L1 regularization. Okay? In fact, when and so this is sort of the two extremes that we get. And so we see we transition here from a kernel type inductive bias that I would consider very boring, which is just L2, to an L1 inductive bias. And again, I think I mentioned this also at the beginning. From my perspective, this is a huge difference, because L1 gives me sparsity. And what I want to do is exactly sparsity. I mean, I want to learn learning features is all about sparsity. It's selecting from an infinite number of possible features just a few features. Okay? And this is what we get here just by controlling the scale. Now, the fact that we have this entire expression means that we can do, this isn't only an asymptotic result. I can do, I can tell you exactly what the regularization is. So if you want to ask, how close are you to L1? How close are you to L2? I'm not going to go, over this math. It's not very interesting. But you can answer basically any question that you want. Right? We have an exact characterization for any alpha. Yes?
Okay, naively, then does it look like for finite alpha it's some sort of Huber loss?
I don't know how to say. It looks like this, right? I mean, it's some kind of. So it's not exactly Huber, but yeah, I mean, it's quadratic close to 0. Okay, so it's not. It's very different from Huber in the following way that. So Huber actually would be linear at some finite place. And this is actually only going to be linear very far. It's actually never going to be linear. So I'm a bit like being imprecise here. It actually looks like b log b, or I think I drew it there, z log z. So it never becomes actually linear. It's only like asymptotically behaves like L1, which is why if you look, okay, I wasn't planning to get into it, but if you look at how small does alpha have to be, you want to get an epsilon approximation for the L1 norm. And you're asking, I want to get epsilon approximation, how small does alpha have to be? I know alpha has to go to 0, but to get alpha approximation, just finitely how small. And the answer is that it has to be infinite, exponentially small. So the dependence on alpha depends on something to the power of 1 minus epsilon, okay? And so that's very different from the Huber loss. It's sort of much less capturing. You really have to work hard to get to L1, unlike Huber, where you get there like the moment you leave 0. Okay. Okay. Sorry. The Huber loss is quadratic around 0 and linear after some point, and you choose that point so that the first derivatives match. Okay. So it's a smooth. You have a continuous first derivative, and the second derivative changes from 2 to 1. Okay. 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 So, but again, just to emphasize the point before, this means that even with finite alpha, I can solve sparse regression problems. Just what do we have here? A sparse regression problem. So this is a problem. We have just a linear problem, because remember that in beta, in function space, we're just talking about linear functions. But this is a sparse regression problem, right? So we have high dimensions, okay, sort of high dimensions, but 1,000 dimensions, but many more, much fewer observations dimensions, only 100 observations for 1,000 dimensions. A kernel method has no chance of solving this. A kernel method cannot, no kernel method can solve a sparse regression problem. You can provably not solve sparse regression with less than number of observations, less than dimensionality with any kernel method. And indeed, we see that when alpha is large, what you should oops, sorry, over here. Just look at the left plot. When alpha is large, what I'm plotting is the population loss. So I do find 0 training error, sure, but what's my generalization error? What's my population error? And unsurprisingly, I can't do anything. But once alpha is, it doesn't really have to be this exponentially small. Once alpha is like moderately small, then I already start being able to be close enough to L1 to solve this sparse regression problem. Okay? I can definitely fairly easily escape this kernel regime. Okay? Just also to the point that Florent mentioned, getting to the L1 is actually very difficult. So you can ask, how much do I pay for the fact that I'm actually not getting to, I'm not doing L1, I'm doing something that's only approximately L1. So what we're asking here is we want to solve a sparse regression problem. And we're asking how many samples do I need to solve it as a function of alpha. Or actually the way we're writing it here is for given a number of samples, how small does alpha have to be? So this number of samples is in the x-axis here. This blue line is what I can do with L1. So with L1, I'm only going to need something like, I don't know what this reaches here, like something like 20 samples. And if I'm really just the exact number of samples that I need with L1, then I really need alpha to be exponentially small, like much, like basically infinitely small. But if I'm just above that, alpha really has to be very small. I can't even get there, numerically. I mean, alpha really has, to be too tiny. Okay. But once I have a bit more samples, still much, much fewer samples than I need with L2, right? With L2, with the kernel method, oops, where am I? Go back. That I want to do on the board. Go back, okay. So it's still, remember that with a kernel method, I need 1,000 samples, right? So it's still much, much fewer than I need with a kernel method. But once I have a reasonable number of samples, then I don't really need to do L1. Even doing this, Q alpha for some reasonable alpha is already okay. Okay, does that also, I think, answer your question? Okay. So good. So we understood the implicit bias here, but and so we already answered one of our questions, which is how does this relate to kernel methods, right? We see that we can get something very different from a kernel method, and the controlling parameter we saw here is initialization scale, right? We'll see a few more controlling parameters in a second. But before that, another thing I want to do is I want to relate this to the discussion we had in the last lecture. Like, can I actually directly identify the dynamics in in function space, okay, and directly say, get an answer for the implicit bias directly from studying those dynamics, okay? So can I go back to the board? Yeah. I guess I'll just leave this connected, right? And you, yeah, okay. Okay, so let's, okay. So what we want to get at is, so I erased all this, right? We don't want to, we're now forgetting that we actually derived the implicit bias, okay? We're going to start all over again, okay? And the way we're going to do it, so, right, we forgot this also, right? So all this we forgot, okay? And what we want to do is write directly how do the dynamics looks like in function space. So function space would be beta. So we want to look at d beta dt. Okay? And let's just remind ourselves this is going to depend on alpha, although I'm not going to bother writing the subscript alpha all the time. Okay? The alpha is just a scale of initialization. So what is d beta dt? Okay? So again, we're going to apply. Actually, let me do it on the other side of the board. Okay, let's do it here. Okay. So what is d beta dt? I can just write again. I'm going to apply chain rule, and this is just d beta dw times dw dt. Okay, and so so what's d beta dw? So let's just even think of it for a generic model. We'll get back to this squared parameterization or diagonal neural net model in a second. Let's first do the development for any parameterization. Generally, I have a parameterization. Beta is equal to, oh, we just erased it, but let's write it here. For any parameterization, beta is equal to f of w. Okay? So this is just the Jacobian of f, right? D beta dw is the Jacobian of f. I'm actually going to just, I'm going to use, you'll allow me to just use nabla to denote Jacobian as well. Okay, so this is, but remember this is a matrix, okay, because where f is a function from a vector to a vector in this case. So it's a Jacobian of f. I think I have to take transpose here, right? Times w times w dot. W dot we know what it is. It's negative. Actually, I'll just write it here. Minus gradient of the loss with respect to w. Okay. But what's the gradient of the loss with respect to w? Right. We want to get this as a function of beta. So again, we'll apply the chain rule here, and we get that this is, well, move the minus to the outside now. We have the Jacobian, and this is applying chain rule. It's again dw. It's the gradient of the loss with respect to beta. Oops. Which is the gradient of the loss times the again the Jacobian of beta with respect to w. Okay, so we have another Jacobian here. Okay. Right. Okay, but let's just move the parentheses around a bit. And okay, and this starts looking very similar to what we had before, right? So we can interpret this as Riemannian gradient flow, where this outer product of Jacobians, or really it's a product of two matrices, but this product of Jacobians is our metric tensor rho. Okay? Right? So we can see that directly how choosing a parameterization gives us a certain geometry of how we're searching inside of inside function space directly. Okay, and function space here is linear functions. It's beta. Okay, and it's the geometry is just given by this outer product of Jacobians. Okay, so now we have two problems. Okay, so we can. Okay, so let me ask you what's our first problem here? If I really want to write this in the way we had before, that I have some metric tensor and I'm doing a search according to this metric tensor. Sorry? So I intentionally was a bit a bit vague when I wrote this, okay? But what is this Jacobian? The Jacobian, okay? Both of these Jacobians are the Jacobian evaluated at some WT, right? So this rho, the metric tensor, actually depends on WT. Okay? So let's actually go back to this board and to see this more explicitly, let's see what is the Jacobian here. So the Jacobian of our model, right? It's the gradient of f with respect to W plus and W minus. So it's going to be, okay, now I'm going to get the transposes. I consistently get these transposes always confused. I don't know if you do. I always, when I look at all these Jacobians, I always get confused. I think that I need it with a transpose, right? So I think that Jacobian is going to look like this. It's going to be the gradient of beta with respect to W plus squared, okay? So that's going to be a diagonal matrix with diagonal W plus, right? Because for every, I have every coordinate of beta is only going to depend on one coordinate of W plus. And then it's also going to depend on one coordinate of W minus. Right? So this is a 2D by D matrix. Okay? But this matrix, this Jacobian, depends on W. Okay? And so does somebody see the problem already? What's our problem here? Okay, so again, what I want to be able to do is write this in the same way that I wrote the Renyi gradient floor. Remember we said we endow our space with some geometry, and we have that beta dot is equal to minus rho. This should be inverse. That's not our problem. Exactly. So we want to be able to write it like this. Right? We want to say that in our space of functions, at every point in the space of functions, we have some kind of local geometry. Okay? So our local geometry, we want it to depend on beta, but here our local geometry actually depends on W. And the mapping from W to beta is a many-to-one mapping. Right? We have many ways of writing each beta. Okay? So our first problem is going to try to see whether we can identify, whether we can rewrite this rho just as a function of beta. Okay? So now this depends on the details of the model. I can't do this generally. We'll see two ways of doing that. So in this case, hopefully we'll see two ways. Here this is going to be fairly easy to do. So the way to do it in this model is it turns out as a function of the initialization, there is an invariant here that allows me to always go back from beta to W. Okay? So where is my invariant? Okay, let me write it here. Okay, so my claim is that in this model, if I look at W plus times W minus, right? Yeah. If I look at W plus times W minus, okay, it doesn't change with time. Okay, so it remains invariant for every coordinate. Okay, so this is, maybe I'll write it even explicitly coordinate-wise. Right, so the okay, so this, I'm not going to derive this now. This is, leave some calculus exercises for the people writing the notes, but it's just, you just plug in dw plus dt and dw minus dt and take derivatives here and things cancel out, it comes to 0. Okay? And once we have this, then now we can actually, for each coordinate, we know that w plus times w minus is equal to the same value that we had initialization, which is just alpha squared. And w plus squared minus w minus squared is equal to the ith coordinate of beta. And now we have two equations and two unknowns, and we can solve them. And again, I'm going to leave this as an exercise to people writing the notes. It's just a quadratic equation. And we get that as a function of beta, w is equal to beta plus minus square root of beta squared plus sorry, other way around, square root of beta squared plus 4 alpha to the fourth plus minus beta divided by 2. Okay, so what I mean for that, so this is holds, actually let's write it this way. Okay, so again, this is element-wise, for each coordinate here is separate, and W plus is going to be equal to this square root of beta squared plus 4 alpha squared plus beta, and W minus is going to be to the same thing minus beta. Okay, so you can verify that W plus squared minus W minus squared is exactly beta squared like we wanted. Oh, sorry, this is W plus minus squared. Okay? So the values with the squared. Okay. Okay, so that's good because now we can go back in here, okay, and I'll plug that back in here and calculate what is this rho equal to. So rho, as we said, is equal, rho inverse is equal to just the outer product of the Jacobians. Okay, the Jacobian is written here. Okay, I just need to plug this W plus and W minus as a function of beta into here. Okay, and I'll save you the math, and what I get is square root of beta squared plus 4a alpha to the fourth. Okay, so again, so this is going to be a metric tensor. It's actually just a diagonal metric tensor, so it means that each coordinate is kind of acting independently. So this is not too surprising, right? Our whole model kind of decomposes over the coordinates. And just make it clear, this is a d by d metric tensor. Okay, and we can now identify. We can now. So now we basically identified what is the geometry in function space. So a few comments about that. First of all, it depends on alpha, right? So you see that the metric tensor, it's not really just a function of beta. It's a function of beta, okay, which is our our vector, our current linear predictor, and our initialization scale. Okay, so this is a bit strange, right? It's not that I have kind of like that just the model itself determines what the local geometry, but it's the model plus the initialization actually determines, once I set the initialization, I determine how my local geometry looks at each place in beta space. Okay? Okay, but once we have that, we can understand the dynamics. So first of all, let's just write down explicitly what those dynamics are. So beta dot, okay, is going to be the gradient of the loss with respect to beta, okay, multiplied by this inverse metric tensor, so by square root of beta squared plus 4 alpha squared. And I'm going to not, this really should be a matrix here, but everything is element-wise, so just think of all the operations here as element-wise. All, everything here, the square root, the square, the multiplication, addition, everything here is element-wise. Okay? Okay, so what do we have here? So we said that alpha controls, the scale of initialization controls whether we're kind of like in an L1 or L2 type regime. And we can see this also from the dynamics. We said that if alpha goes to infinity, okay, then the dominant term inside the square root here is going to be the 4 alpha squared. Beta is not going to matter. And up to some scaling which just affects kind of the speed but doesn't affect the trajectory, the dynamics is just d beta dt is given by the gradient of the loss. And that standard gradient flow dynamics would just correspond to L2 geometry. Okay? On the other hand, if alpha is 0, and the problem alpha can't really be 0 because okay, we maybe should have mentioned it explicitly before. If alpha is 0, we're initializing at a saddle point and we're not going to move at all. Okay? But if alpha is 0, then this term doesn't exist, and the scaling we get here is just beta. Okay? And that's exactly this scaling we said corresponds to L1 type dynamics, or something that approaches L1 type dynamics. Okay? That gives us the minimum L1, will give us the minimum L1 norm, right? Because it induces sparsity because in order to change a coordinate, I'm going to be more biased to changing coordinates if they're already very large, and I'm not going to want to touch things where beta is small. Okay? So this doesn't give us, if we just look at this, at least intuitively we can already see the L1 versus L2, but we don't get a quantitative answer like we did before. But we could get a quantitative answer, right? Because we know that in order to get a quantitative answer, all we have to do, okay, is to write rho. So all we have to do is write rho as the Hessian of some potential, right? If I can do this, then I know that the implicit bias is given by this potential. Right? That's what we learned last time. Okay? Okay, so now we get to the second problem. So we said we have two problems of analysis here. The first problem is being able to describe the local geometry, hopefully without, just in terms of where we are, or maybe we'll see later, maybe with the minimal other stuff. The second problem is once we identify the metric tensor, is the metric tensor at all going to be a Hessian map? And if it is, then what is psi? Okay, but I said that in general, it's, a metric tensor in general would not be a Hessian map. In this case, we're in luck because our metric tensor, where's our metric tensor? So our metric, let's go, where's my eraser? Let's go back to this board because now we're talking about this specific model. So our metric tensor, which is diagonal. It's diagonal of, what is it? B squared plus 4 alpha to the 4th to the power of minus half. Okay, we called it what's here is the inverse metric tensor. So this is our metric tensor. And the diagonal function is basically always a Hessian map, right? Because now all we have to do is, since something is diagonal, being a Hessian map just corresponds to having, the Hessian just amounts to taking, looking at second derivatives of the diagonal elements, okay? And so this will be a Hessian map. And in order to identify a Hessian map of what function it is, again, since everything is coordinate-wise, all I have to do is integrate this function twice. So look at the double antiderivative of this element-wise function. Okay? And again, I have no idea how to do that. I forgot how to integrate these things. But fortunately, Mathematica is very good at that. I plugged it into Mathematica. And what you get is that, where's my answer here? Okay, I have my answer here. So, I mean, you get that, so basically you get the same answer from before. We do have a prefactor of alpha squared that doesn't matter, so sum over I of, so the same thing as before, beta over alpha squared times sine, we had it written somewhere, right? I already erased it. Okay. Okay, I mean, I don't know why I'm writing this because it's the same expression that we had before, and anyway, you have to believe me that I actually integrated this in Mathematica, and this is actually, you do get the same answer both ways. Actually, I should say that initially what I found is you don't get the same answer because you have to actually fudge with some hyperbolic trigonometric identities to verify that it's the same function up to a constant, but it is the same. Yes?
So can I just ask, this point of view you're presenting, it seems in general, even if your Hessian weren't diagonal, even if your metrics were diagonal, if the function capital F is harmonic, then automatically this is a Hessian. Right? It's like 1/2 the Hessian of F squared or something because, the Laplacian
okay.
would be 0. I mean, in your case, it is harmonic, it's the difference of these two squares. So it's like...
So, okay, I'd be very happy to talk about it later because you're probably right. In fact, we're trying to, I'm not familiar enough with this analysis. So we're in fact exactly trying to understand in which cases it would be a Hessian map and in which it wouldn't. I'm going to give later an example that's not a Hessian map. So maybe after that you'll see that in that case it's not harmonic, and we can maybe get back to that. I mean, I think that, so in fact, one of the questions that I want to pose, so again, I'm very happy to be here, not only because of the mountains, but also part of my reason for giving these lectures, especially this lectures, there are a bunch of things here that I don't understand, and I think many of you guys can understand much better than me. And this is one such example. So yeah, I'll be very happy to talk about this. So this is something exactly we're trying to understand. When can we actually do this and when we can't? Okay, and we see that. Okay, I'm not going to have time to talk about it, but sometimes we have to do all kinds of tricks also. Even if it's not a Hessian map, we can kind of multiply it by some scalar that doesn't change the trajectory, and then it becomes a Hessian map, and do all kinds of tricks like that. And we're trying to understand what's a general kind of recipe here. Okay, okay, okay. Good. So yeah.
Sorry, should that be psi beta, this latest thing you wrote? No. Psi.
Where?
Not the Hessian.
No. This is psi. This is psi beta. Yeah. Sorry, that's after I double integrated element-wise. Thanks. Okay. Let's. Okay, actually, let's go back to the, okay, so just see where we are, but we'll go back to the slides just so I can be a bit quicker with this next part. Okay, so good. So what we saw already is now two different ways of how we can derive the implicit bias, either by looking things directly or by just identifying the dynamics and then using kind of the recipe. I want to, just before moving on, just a small, it's going to work, right? A small depth. So we also saw, so we said that we saw how to get to the kernel regime when the scale goes to infinity. But another way to get in the kernel regime, I know, is when the width goes to infinity. Okay? So how does that fit into this? So let's try to understand it. And again, I'm going to look at, this is a completely stupid model, but stupid here is a good thing, right? It's kind of the simplest model in which I can already see width. So what I'm going to do is I'm going to take my same linear diagonal network, and instead of having just one or maybe two units for each coordinate, I'm now going to have many units for each coordinate. So I'm going to increase the depth. Again, this is, it's just implementing a linear function. So again, this is just a parameterization of a linear function. But now this is kind of a wide parameterization of a linear function. Right, so formally now, right, so the way I'm writing my function beta is the diagonal of u times v, where u and v are matrices, right? So I have for each coordinate, for each coordinate I have a vector vector ui and a vector vi, and I'm multiplying these vectors together. Okay, is this model clear? Okay. Okay. So now what happens in this model? So we could actually go through all the analysis. Again, I'm not going to go through all the analysis, although if you want as an exercise, you can do it. But basically, the way that okay, actually. One more thing that's important here. Sorry, I have to tell you how I'm going to initialize it. So now I can't initialize them all to be 1, because before I just initialized everything to be 1 and it was fine. Now if I initialize everything to be 1, it's going to be degenerate, right? Because if everything, if this vector is a vector of all ones, this vector is a vector of all ones, because of symmetry, nothing is going to move here, nothing is going to change. Okay? So instead, the way I'm going to initialize it is random, and the question is random with what scale? Okay? And the way I set my scale here, so we're just going to initialize everything to be Gaussian with some variance sigma. But I'm going to choose sigma in this particular way. I'm going to scale it by the width. K here is the width. It's the number of units per coordinate, to ensure that my output variance is alpha. Okay, so before, right, right, so, and this is the way I like the scaling is because it's a scaling that's kind of independent of the parameterization. It's a scaling of the function itself, of beta itself. Okay, so that's how I define alpha here. And as we'll see, this is going to, okay, sorry. And the question is what's going on here. And we can actually apply the same analysis before, but we have to be a bit careful. So what's going to happen here is that if we're going to look at the dynamics, I can't actually write the dynamics just in terms of in terms of beta. What I have to do is kind of lift the problem. And this is an example we'll see here also before. So we have to look at this symmetrized problem. So instead of just looking at UV transpose, we're going to actually look at the entire matrix of the parameters times themselves. Okay, so think of W as a matrix which is just containing U and V. So we're going to look at the entire matrix UU transpose. So in the off-diagonal blocks here, I have UV transpose, which is exactly what we're actually using. So my observations are actually only going to lie on these inverse on these non-diagonal blocks. Okay, but I will actually keep track on the entire thing. And the reason that's important is it turns out that when I look at the scale, when I plug this into analysis we had before, and look at what is the relevant scale, the relevant scale is not just the scale of these off-diagonal blocks, which is alpha squared, but the scale of the entire matrix W. Okay? And since U and V are chosen to be random, then UU transpose has a much higher scale than UV transpose. Here I'm taking outer products of independent random vectors, whereas on the diagonal of W, I'm actually taking inner products of a random vector with itself. I'm looking at the norm of random vectors. Okay, so they're going to be larger by a factor of square root of k. Okay? And so now, the relevant scale becomes not alpha squared, but square root of k times alpha squared. So I realize I'm not going over the details, but I hope at least intuitively it's clear what's going on here and why the scaling, the relevant scaling is much larger than the observed scaling, the scaling of the observed parts. Okay? And when you go through the analysis, you get that again, this scaling now determines whether you're in the kernel regime or not in the kernel regime. In particular, you can work out the implicit bias here, and again, you can do this exactly. Exactly when k goes to infinity, and the limit when k goes to infinity. And what you get is that you depend on this this q alpha, this same q function, where now instead of scale alpha, it's scale alpha times. So it's okay. So before it's actually mu. Does it? If you recall, before it actually would have your alpha squared, so it's the scale here is square root of k times alpha squared, so we take the square root of that. Instead of alpha, we get alpha times the fourth root of k. The point here is that because of the scale, if you think of k goes to infinity, okay, so again we identify as before when mu goes to 0 in the L1 regime, when mu goes to infinity, we're in the L2 regime. But the important thing now is to say whether mu goes to 0 into infinity, what we have to look at is whether alpha is larger or smaller than the 1 over the fourth root of k. Okay? So that means that as long as alpha can actually go to 0, but if it goes to 0 slower than 1 over the fourth root of k, where k is the width here, then my effective scale actually goes to infinity. Okay? So I can, even with high width, ensure that I'm in the rich regime, but in order to do that, the scale of initialization has to be very small. My effective scale has to, so not only does, I have to, my scale has to go to 0 and has to go 0 adequately fast. Remember, the scale we're looking at here is the scale of the outputs, not the scale of the weights, right? So that means that in order to be in the kernel regime, I have to initialize to really something that looks like zeros at the outputs. Not only zeros, but like fast zero, like very small zeros. Zeros that are smaller than 1 over fourth root of k. Okay? And I think this is related also just as a comment about the Haim's lecture. I think Haim is not here, but I think somebody also brought it up, that the scale of initialization here is somewhat related to this sigma squared parameter that Haim had, the how much you control because that controls the scale of your weights. And you got into this kernel regime or Gaussian process regime when you let the width go to infinity while keeping this scale fixed, keeping sigma squared fixed. Okay? And that, in this case also, if we keep alpha fixed and take k to infinity, we'll be in the kernel regime. Okay? But if you take them, you can take a proportional regime here, and the right proportionality is given here. The alpha is to scale is fourth root of k. If you do that, you can avoid being in the kernel regime even when you take the width to infinity. Okay, let's just go. Okay, so the next thing, next question. So we hopefully understood how something about the kernel regime and how we go into the kernel regime or not, both in terms of scale and width. The other question we said that we want to answer is the implicit regularization just the same as L2 regularization in parameter space? Okay? And so we can actually just ask the question explicitly, what will we get here if we do explicit L2 regularization in parameter space? So now forget dynamics. So again, now we're doing We're being, what did Heim say? We're being patient, right? So we're doing exhaustive search. We don't care about the dynamics at all, right? There's no initialization. Okay, he's not here, but in what we're just defining, but we're just looking at what would I get if I looked at a zero error solution that had minimum L2 norm, but not exactly minimum L2 norm, because we still want to think of the scale of initialization. So it's no longer initialization, but we want to do the minimum L2 difference from our initialization, right? Because that's kind of what we think we get like with gradient descent. We get the minimum L2 distance from initialization, right? So we're looking at the effective model, the model we'll get if we look at the weights that fit the data and minimize the L2 difference to just being all alpha. Okay, we can think of this function as this is our representational cost, right? How far away from alpha we have to be. And representational cost when we think of the origin as alpha. Okay, this is representational cost on W. This induces a representational cost on beta, which is what we're effectively minimizing when we're minimizing the L2 distance from all alpha in parameter space. Is this clear? Okay, maybe. Okay, so this maybe I'll say this again a bit clearer. So this representational cost is something whenever we have explicit regularization in parameter space, and we want to ask how does this explicit regularization in parameter space affect what happens in function space, then we have to ask for each function in function space, what is it the regularization cost of the cheapest way of implementing it in parameter space, which is what we're asking here. And now we can ask, is this function R beta the same as Q beta? Is the function R the same as a function Q? Okay. So we can actually calculate this function Q R directly, again, thanks to our friends in Wolfram Research. So R, this is just, we have to solve a minimization problem, but it's just a minimization problem over a fourth order polynomial, so that we can do in closed form, or Mathematica at least can do in closed form. And it turns out that R is, again, an element-wise function, and the regularizer I apply to each coordinate is given by the solution of this quadratic equation. Okay, and if I had 2 more pages of slides, I can actually write you this closed form of this quadratic equation. I don't think it's going to do anybody any good. The question we want to ask is this the same as the Q function? Okay, so without actually showing you any plot, you can already tell you that this is not the same. This is an algebraic function, right? So it's just the solution to a quadratic equation is algebraic. It's just going to be a very large expression with a bunch of square roots and higher order roots, whereas the expression we had before involved a hyperbolic sign. It's definitely not, it's not an algebraic function. So we already know that they're not the same function. We can plot them, and okay, we can see that they're not the same function. They look, okay, so in particular, going back to Florent's question, the R function, which is in blue here, actually looks a bit more similar to the Huber loss, like it gets to L1 actually a bit faster, okay? But still, it's not exactly the same, but come on, I mean, the blue, without going into the details, or if I showed you the picture of the red function and the blue function not on top of each other, just separate, you wouldn't be able to tell that it's not the same function, right? I mean, qualitatively, you can get into the weeds and talk about some qualitative differences, but it looks the same. It interpolates between L1 and L2. So where we see a bigger difference between implicit regularization, to see a bigger difference in implicit regularization and explicit regularization, we have to go to depth. Okay? So again, we want to, up until now we talked about depth 2 models, or homogeneous of degree 2. Now we're going to go to deeper models, and again we're going to do it in the simplest possible way we can, which is just a deep diagonal network. Okay? So in other words, maybe it's easier to think about it this way. Instead of having a squared parameterization, we just take it to the order d, and okay, maybe to be, it doesn't matter too much. If d is odd, then you should maybe add an absolute value there, although it turns out to not matter because it's not going to cross 0 anyway. Okay, or just think of d even if you prefer. Okay, and now we can again ask what's the implicit bias here, and how are you going to do it? Well, we can do the exact same thing we did before. Since I am completely running out of time, I'm not going to do the derivation carefully, but basically we do the exact same trick. We follow the exact same recipe we had before. For example, we can do it explicitly by writing equations for W plus and W minus in terms of the residuals, solving them in terms of integral for residuals, plugging into beta, and what we get is this expression for beta. And again, beta is, this is just some solution to in this case polynomial differential equation, which Mathematica is happy to solve for me. And the details here are not important, and the only thing important is, again, beta is always a function, some function of this integral for the residuals. And I don't know what the integral for residuals is, but it doesn't matter. It's just an m-dimensional vector. Okay? So that means that beta definitely lies inside some m-dimensional manifold. So in both of these cases, we could identify that no matter what the residuals are, I'm always in this. I'm always stay inside an m-dimensional manifold. I can cross this m-dimensional manifold with being in a global minimum, and now I want to match this against the KKT conditions for some problem. Again, I want to find what this Q function is. Okay, and to find it again, this is still a coordinate-wise or a diagonal function. So all I need to do is invert this function and integrate it. Okay, so at this point, Mathematica failed me. Mathematica cannot actually integrate the inverse of this function. But fine, okay, so it's probably my guess is there's no a closed form solution here, but it doesn't really matter. It's just, I mean, even saying that, before the only reason we had the closed form solution is because somebody decided to give a name to the hyperbolic sine function, right? It's not like it's not special in any way. It's still a function. It's a well-defined function. We can work with it. We can analyze it. We can take its Taylor expansion and see how it behaves. Okay? And so the way it behaves is as follows. So what I'm plotting here is, so again, the implied regularizor, when I do this dynamics for some depth d, the implied regularizor is going to be an element-wise this QD, where QD is an element-wise regularizer, which applies to each coordinate some function little qd and scaled by alpha d. Okay? And what I'm plotting here are the functions little qd. So the regularizer applied to each coordinate, okay, for different scales. So depth 2 through depth 15. Okay? And what we see from the plot, and what you can also verify, is all of these functions are quadratic around 0. Okay? So all of them have a positive second derivative, 0 first derivative, and positive second derivative of 0. So all of them are quadratic around 0. Okay, that part is not surprising. What that tells us is for all of them, if you take alpha to infinity, you're going to be in the kernel regime. That we already knew before. We really didn't have to do all this for that. Okay? The other thing we can see is that all of these functions are actually asymptote linear away from 0. Okay? And actually, for depth 3 and on, it's really linear. It's not z log z. Okay? So that means that no matter what depth we take, if we take the scale to 0, we only care about what happens. Oh, this is even better. All we care about is what happens far away from. That was pretty cool. I didn't know how that happened. What we care about is only what happens far away from the origin, which means we have L1. So for any depth, the effective regularization when alpha goes to 0 is just L1 regularization. And here is where we see a big difference versus explicit regularization. Because we can also ask this question, the exact same question just we did before, with explicit regularization. So again, we look at the representational cost, but now we'll look at the representational cost of, okay, I do want to get it back. Okay, we do look at the representational cost of not, what's the cheapest way in terms of L2 distance from alpha of representing a predictor beta, where beta is of this form. And it's not too difficult to see that what you'll get here is a quasi-norm which goes with an exponent that goes down with the depth, as 2 over the depth. Right? So what is the cheapest way to represent this? So roughly speaking, if alpha goes to 0, right, then this doesn't exist. And you definitely don't want to make both W plus and W minus negative. You only want to make one of them non-negative. You want to only make one of them non-zero. Let's just think of beta being positive. So forget about W minus and we just have W plus. So W plus is just going to be the dth root of B. And we're taking the L2 norm of the dth root of B. And so you get the sum over the each coordinate of B to the power of 2 over D, okay, which is exactly this 2 over D quasi-norm. And that's very different from L1 norm. Okay, so we actually see that with the implicit regularization here is very different from explicit regularization in a qualitatively significant way. Okay, I'm in trouble, huh? How much time do I need? More than I have because I have 0, right? Let's. But Sarah is speaking at 4, right? I can't just go on. I mean, these guys need a break also inside. like half an hour, but I don't want to take half an hour now. Maybe, can I, seriously, maybe I'll finish and I'll do another 10 minutes now and finish on Monday? Is that? Okay. Okay, I do want to finish because we're getting close to, I need like another half hour to get to the punchline. Let me just take a few more minutes now and then we'll finish on Monday. Is that, or do you want to just continue on Monday? Up to you. Sorry? Just continue on Monday? Okay, good. So I'll take one more minute now and continue on Monday. Okay. Okay, so, so another difference we're going to see here, and this is, we're going to look at that more on Monday, is we see here a difference in explicit regularization and implicit regularization. And another difference we're going to see, and that's what we're going to maybe start talking about on Monday, is the difference between the squared loss and the logistic loss. So all our discussion today was just about the squared loss. And actually, it's not really important it's a squared loss. So since all we needed in all of these, we didn't really care about the residuals. All we really needed was that the dynamics is given as some function times the data. Then all we needed is we didn't really care about the loss. The dynamics, the characterization of the manifold is completely independent of the loss. So the only way we really use the loss is to say that when the loss is 0, we have that. We don't know, it was behind the board. We need to say that when the loss is equal to 0, then x beta is equal to y. That's the only way we use the loss. So really the only property of the loss we need is that it has a unique minima and exactly at unique minima exactly at the data. Okay, or exactly at the correct label. Or really, it doesn't really matter what it is. All we need is a loss with a unique finite minima. But the logistic loss is very different from that. Right? The logistic loss doesn't have any minima at all. And what we'll talk about on Monday is how for the logistic loss we get a qualitatively very different behavior, in particular in this setting of a deep neural network. Okay, so I guess we'll wrap up today and I'll see you for a makeup lecture on Monday. Thanks. So Lenka, is it, oops.